So our next speaker is Dr. Abebe Tufa from the University of Botswana. And the title of his talk is Iterative Methods for Finding Fixed Point of Enriched Non-Self-Mapping in Hilbert Spaces. So Dr. Abebe, you can now start.
Okay, thank you very much. Good morning, good evening, and a good afternoon for everyone. Thank you very much for the organizers. I really appreciate this because really this is very good to share our experiences. I really learned a lot from this presentation. It is a focused one. When we attend conferences, many of the time the fields are different and sometimes we get lost. But I think this is very intensive and focused we are all from similar fields. I like that and I learn a lot from this conference. So I would like to thank the organizers.
You're very welcome.
Having said that, my topic is iterative methods for finding fixed points of enriched non-self-mapping in Hilbert spaces. I think almost all the presenters before me was talking about in general non-expansive, I think nonlinear mappings, and they all discussed about fixed points. If it is equilibrium problems, for example, they also talked about fixed points in there, how it involves in other fields. And I think Prof. Saha in the first half of session explained very well about contraction mapping, Picard iteration, which makes my presentation very smooth here because I will focus on very few literatures, which is very related to our findings instead of doing all, because it has done already with some of the presenters. So my outline is this. I start with the background of the study with basic definitions and notions. But like I said, I will not waste more time on this because it is discussed in all the presentations. I will present some literatures which are very related to our results and then purpose of our study. Then under main results, we focus on two important mappings here. Iterative methods for finding fixed point of enriched strict pseudo-contractive mappings and iterative methods for finding fixed points of enriched quasi-non-expansive mappings. Then I will give summary and future works and numerical examples. Like I said earlier, the theory of fixed point is discussed in all the presentations. No need to talk much on this. And we all know that problems which can be formulated and studied as fixed point problems include variational equality problems, like all of the presenters, especially variational equality problems also related to what Dr. Sangago was talking about, optimization problems, system of equations, economic equilibrium problems, and many others. So I will first present the classical mapping is known in a fixed point theory. The contraction mapping, I excluded it because it is discussed nicely in the first half of the discussion. If C is a non-empty subset of a real Hilbert space H, then we say that the mapping T from C to H, and then self-mapping is non-expansive if the norm of Tx minus Ty is less than or equals to norm of x minus y for every xy in C. And we call it quasi-non-expansive mapping if the fixed point set of T is non-empty, and this inequality here holds true for all x in C and all p in fixed point sets of T. And we say that the mapping T is K strictly pseudo-contractive mapping if there exists a positive number K, which is between 0 and 1, including 0, such that this inequality holds for all x, y in C. And as we can observe from here, non-expansive mapping is also quasi-non-expansive mapping when the fixed point set is non-empty. So quasi-non-expansive mapping is more general than non-expansive. So because every non-expansive mapping will be quasi-non-expansive if the fixed point set is non-empty. And the case 3 pseudo-contractive mapping is also an extension of non-expansive mapping because it reduces to non-expansive mapping when K is 0. But quasi-non-expansive and the K-strict pseudo-contractive mappings are independent. So these are classical mappings, which is very known, but recently the following class of mappings, which generalizes the above mappings, are introduced. This mapping is first introduced by Brande. The first one is B-enriched non-expansive mapping. It is a mapping, non-self map. We extend it to non-expansive mapping. Brande defined it for non-self mapping. If T is a mapping from C to H, then we say that this mapping is B-enriched, non-expansive, if there exists a positive number greater than 0, including 0, such that this inequality here holds true for all x, y in C. And we say that this mapping is B-enriched quasi-non-expansive if the fixed point set of T is non-empty and there exists a B bigger than or equals to 0, such that this inequality holds true for all x in C and for all P in the fixed point set of T. And we say that it is BK, strictly pseudo-contractive mapping, if there exists a B greater than or equals to 0 and K between 0 and 1, including 1, such that for all x, y in C, we have the inequality here. So these, in general, these are extensions of the above mapping, and we can see that the B-enriched non-expansive mapping is the extension of non-expansive mapping. When B is 0, it reduces to the non-expansive, the classical non-expansive mapping. And the B-enriched quasi-non-expansive also reduces to quasi-non-expansive mapping when B is 0. And the BK strict pseudo-contractive mapping also reduces to the K strictly pseudo-contractive mapping when B is 0. And again, from this, we can easily observe that B-enriched non-expansive mapping is a B-enriched quasi-non-expansive mapping when the fixed point set is different from 0. And the BK strict pseudo-contractive mapping is also more general than the B-enriched non-expansive mapping is. And again, here, B-enriched quasi-non-expansive mapping, the BK strict pseudo-contractive mappings are independent mappings. We normally have examples which is B-enriched quasi-non-expansive, but not BK strict pseudo-contractive mapping, and vice versa. So our focus is on these mappings. Mainly, we focus on the second one, B-enriched quasi-non-expansive mapping, and the BK strict pseudo-contract mapping, which means when we deal with these two, indirectly we are dealing with also number one, which is a B-enriched non-expansive mapping. So as we all know, the theory of fixed point, like it is explained well in all the presentations, is applicable in various fields, but there is no standard method to find the fixed point of nonlinear mappings. That is why we are all focusing on iterative processes to approximate fixed points of nonlinear mappings. So the first one is Picard iteration normally, which is given like this. Like I said, this was discussed in detail in the first half of the session. So I just leave this one. So the other one is the Banach contraction mapping principle, which is the most celebrated result in fixed point theory, but it does not apply for this one. Non-expansive mapping when even the fixed point exists. That one is only for contraction mappings, and that is why researchers in the area were looking for other algorithms to approximate fixed points of more general than mapping is more general than contraction mapping is like non-expansive mapping is. So in 1953, Mann introduced this iteration method, which gives weak convergency for non-expansive mapping in infinite dimensional space. So in this case, we now only this algorithm gives weak convergency. Then people were working on this problem to obtain a strong convergency, among which help Alpern, Ashikawa are very known to give a strong convergency for non-expansive mappings, and even Ashikawa for pseudo-contract mappings. So the other line of research, which is recently introduced, is now when those classical mappings like non-expansive, strict pseudo, pseudo-contractive, all of them are extended by introducing a new mapping called Enriched mappings. So Brande introduced the class of enriched non-expansive mapping and the class of enriched strict pseudo-contractive mappings. And it has been shown that every enriched non-expansive mapping is defined on subsets of Hilbert space as fixed points, which can be approximated by the Krasnodębski iterative methods under mild conditions. It is shown in Brande's papers. So here he obtained weak and strong convergence results for approximating fixed points of enriched strict pseudo-contractive self-mappings in the Hilbert space setting. On the other hand, Shukla and Pant introduced enriched quasi-non-expansive mapping motivated by the results of Brande. Okay, they were motivated by the results of Brande, and they introduced enriched quasi-non-expansive mapping, and they obtained a weak and strong convergence results in the setting of Banach spaces. However, all the above results are for self-mappings. For the algorithms are well defined only for self-mappings. So what people were doing is they employ metric projections to deal with algorithms which defined for non-self-mappings. But competing projection mapping is computationally very expensive and very difficult in practical applications. So to overcome this problem, Coelho and Marino in 2015 studied the following algorithm. They studied this algorithm. Instead of projection mapping, they introduced a function like this, h of x infimum of lambda greater than or equals to 0, such that lambda x plus 1 minus lambda tx is in C for all x element of C. And the T is non-self-mapping. So this h of x controls now everything in C. Then using this algorithm, they obtained weak and a strong convergence algorithm to fixed point of non-expansive mappings under some appropriate conditions. And this result also extended to k-strict pseudo-contractive mappings by Kylo and his co-authors in 2017. To obtain strong convergence in the above result, these authors used the following definitions. They used the definition of inward mapping. T from C to H is inward if it satisfies this condition here. And they also defined a K. This K is supposed to be C, sorry for that. C is said to be strictly convex. If it is convex and with the property that for all xy in the boundary of C, this is supposed to be C, and the t is between 0 and the y, then tx plus 1 minus tx is in the interior of K. In other words, if we pick 2 points on the boundary of the set, the line segment between the points should lie entirely in the interior of the set. So now they used these results and they posed a question there uh, if it is possible to adapt that algorithm for a family of mapping. This one algorithm is the iterative scheme here. Coelho and Marino posed a question if it is possible to adopt this to multi-valued mappings. In When they try to extend this one to answer this one, this author Go, I don't know how to pronounce, Go et al. Introduced the following. To adapt that algorithm for finite family, family of mappings, sorry, family of mappings, they defined this definition here. If we have D in the C, two closed convex non-empty sets in a Hilbert space H, and the D is a subset of C, then any sequence, for any sequence Xn in C, if Xn converges strongly to an element X naught in the boundary of C, not in D, such that Xn is different from X star, implies Xn is not fidget monotone with respect to the set D. Then we say that the pair D comma C satisfies the S condition in this case. I think we all recall the definition of fidget monotonicity. It is given here. Then using this definition, they have managed to obtain weak and strong convergence of Coelho and Marino method to common fixed point of countable family of non-self mappings. Now our objective is to construct a new iterative methods that are well defined for non-self mappings without using the projection mapping, and to establish weak and strong convergence results for approximating fixed point of enriched non-self mappings under some appropriate conditions. This is motivated by the literatures discussed above, especially Brande and Moreno. Brande is for non-self mapping, Moreno for non-self mapping, but for non-expansive and K-strict pseudo-contractive. We want to extend that one to enriched non-expansive, quasi non-expansive mapping and enriched strict pseudo-contractive mappings. So we started with this algorithm. We introduced the following algorithm for non-self mapping. Enriched strict pseudo-contractive mapping. A is between 0 and 1. Beta is between 0 and 1 minus K. And lambda is 1 over B plus 1, where B is the B we have here because of B K enriched strict pseudo-contractives. Then our algorithm is given like this. So using this algorithm, we have proved the main result here. This is one of our main result. If C is non-empty closed in convex subset of a real Hilbert space H, T is non-self, BK enriched strictly pseudo-contractive inward mapping with F of T non-empty, then the sequence generated by the algorithm we have discussed above converges weakly to a fixed point of T. Moreover, if C is strictly convex, if we use the strict convexity defined by Marino and Colino here, we obtain a strong convergence when the summation of 1 minus alpha is finite. So the proof is too long and very technical, but I have the sketch of the proof here. What we did first is the limit of xn minus p, where p is in the point set of t exists, and the summation here is finite. And then we considered two possible cases from the theorem. If the summation of 1 minus alpha is finite, infinite, Then using some known properties of mappings in Hilbert space, we obtain a strong convergence of the algorithm to a fixed point of the given mapping. And if the summation of 1 minus alpha n is finite and C is strictly convex, we obtain a strong convergence of the algorithm. That is the sketch of the proof. As we can observe from the algorithm, if the mapping is K strictly pseudo-contractive, it means B is 0, so we call it 0K enriched strict pseudo-contractive, and our algorithm reduces to this one. Lambda is 1 in that case, so we obtain this algorithm for K strict pseudo-contractive mapping. That is special case of the main algorithm, and we have this theorem, which is a special case of the theorem we have just discussed. So for quasi-non-expansive mapping, we introduced this one, that is for approximating fixed points of enriched quasi-non-expansive mappings, and we suggest this algorithm, and using this algorithm, we have proved this theorem, theorem 5. But before that, we recall the mapping from C to H is said to satisfy condition I if there exists an n-decreasing function f from this set to this with f of 0, 0 and f of r greater than 0 whenever r is bigger than 0. And the norm of x minus tx is bigger than or equals to f of the distance between x and f fixed point set of t for all x in C. Whenever the distance between x and the fixed point set of t is given like this. Then we use also this in the proof of theorem 5. So this theorem 5 now includes the conditions introduced by Go and his co-authors to obtain a strong convergence of man iterative scheme for countable family of mappings. But for us, we used it for B enriched quasi-non-expansive mapping. So this the sketch of this theorem is also given here. We first show the norm of the sequence given by norm of xn minus p is decreasing sequence whenever p is in a fixed point set of t, and this summation here is finite. Then after that, we considered also two possible cases. The case is when the summation of 1 minus alpha n is infinite, then using condition I in the sum properties of Hilbert space, we obtained a strong convergence of the algorithm to a fixed point set of t. And the second case is when the summation is finite. In this case, we use the S condition and the inwardness property to obtain strong convergence of the algorithm to a fixed point set of t. So in this case, in both cases, we obtain a strong convergence. So we have many special. Okay, thank you very much. So we have many special cases for this one also. Let me leave those special cases. And we have also numerical examples here, which is on R. Here, this is just a simple example to see how the algorithm works. And we have also the graph using MATLAB here. But what I want to like to point out here before I close my talk is based on Sangago Mengistu's, Dr. Mengistu's question for Dr. Hagos. I was saying that the examples we give here are lower standard, but our theory is very abstract. I agree totally with that. But I think we are starting now because many research findings was without examples before, but people is starting now doing examples. I think we are starting. It is good to start, but we should work hard, all of us, because it is not easy to write algorithms when it is abstract, but we should work on it. I agree with that. And my example is also on R, which is very low standard when we compare to the abstract Hilbert space. That is all, and the summary is here. the summary is normally the extension. Our result is extended, many results in the literature. One of them is Brandes results, which is in enriched non-expansive mapping. We extended that one to enriched quasi-non-expansive mapping. The other one is enriched enriched strict pseudo-contract mapping. We extended that one to non-self mapping in both cases, non-self mapping. Also, Moreno and De Coelho, the result is for non-expansive and strict pseudo-contract mappings. Ours is enriched and enriched non-expansive and enriched quasi-non-expansive and enriched strict pseudo-contract mapping. And many others in literatures also improved or supplemented by our findings. And as future work, we can extend these results to Banach spaces more general than Hilbert spaces, even in non-linear spaces like Harmard spaces. And we can also extend it to a point to mappings more general than quasi-non-expansive and strict pseudo-contract mappings, like general pseudo-contract mapping in the others. It is also not known if we can adapt our proposed algorithms to family of mappings. I think we can work on it, and any interested can work on it also. I learned also this morning Canaan enriched mappings. This gives me also to look at if our proposed algorithm for works for Canaan enriched mappings. These are the references we used. Thank you very much.
All right, thank you, Dr. Ababar Tufa. Let us thank our speaker.
Thank you so much for the nice presentation.